have I/O traffic going to my swap device. So SAR-W, I've got pages swapped in, pages swapped out, blocks swapped in, blocks swapped out, 512 byte blocks. The one you don't want kicking up is blocks swapped in, because that's an indication that you're waiting for data on your swap device. I don't have a problem with blocks swapped out because I could zero out an array and then push it out to swap and never use it. And that overlaps, it doesn't impact the performance of my system unless that swap out traffic is going down the same channel as my root device or home or something like that. And I'm not sure why they've highlighted the process switching one. These four are the way we time slice memory. The last two are the way we time slice CPUs. And this is context switching or process switching. So every time I go into the kernel due to a clock interrupt, I have to decide who to switch back to. P switches are switching back to user programs. K switch is switching back to kernel threads. And this is new in Irix 6.5. But for example, vHand, if I have a lot of vHand activity, you'll have a lot of context switches to K switches. And they may actually get higher in this case than the context switches to user space. So these two are just saying, how often do I time slice my CPUs? And then these are time slicing my memory. And I think we'll be coming back to process switches later. But common kernel switches are to BD flush. If I got a lot of dirty data I'm writing into cache, BD flush will be waking up, or vHand, or shake D. Those are the common kernel switches that we're talking about. SAR-T, even though it's listed in here, I have never found any use for it. Okay. This is describing my translation look-aside buffer activity, but I find the previous two options to be much more useful. The only time you get into SAR-T might be in the real-time market, virtual reality. When you're tuning, you're starting off with a big picture, but eventually you're getting down into event-by-event latency and saying, well, why did this thing not handle something? Because it got interrupted due to something else. So with this SAR-T, I tell people not to worry about it. But T-faults are simply saying the address is not resident in the TLB. R fault says that the valid page is in memory, but there was this page reference fault, a hardware valid bit disabled to emulate a hardware reference bit. There's a sync operation that says all TLBs on the system are going to get flushed. And that's used in page migration, so we're going to flush all the TLBs on all CPUs. And then there's this VM wrap, syncs caused by a clean kernel virtual memory depletion. Single processor flushes depleted, new TLB IDs issued or purged, and individual TLB entries purged. Now again, you're not going to see a whole lot of activity in any of these. The only one of interest here was a whole lot of flushes and some sinks. Okay, and a lot of them are just coming out as 0. And I really don't have much more about SAR-D. Being a Cray person, they have very little meaning to me except when I'm down to an event-by-event situation. Process size is printed out with PS. There are a couple other ways of getting it as well, but with PS we've got these two fields, the size and the RSS. The size is the virtual size that is asked for, and then the RSS size is what's physically in memory. And some of that space may not be used at all. I might have mallocked but never referenced the pages. Or I could have referenced it and they may be sitting out on swap. There's no way of actually saying whether the difference between the two is usable data or not. I actually have a little script that takes this, divides the difference between, or takes the difference between them and then sorts it to give me the top virtual swap hogs, the things that have the largest spread between RSS and physical size. Okay, so for example, let me go off to do. It just took that PS command and sorted things and then figured out basically, for example, I've got LS Dyna running on this machine right now. Got a couple multi-threaded versions of Dyna, and this is saying how much space is difference between my RSS and my virtual. And let's see if swap-ln. We do still have some reservations going on with 3 of those devices, or at least sitting on one of them. Not much though, maybe a meg of allocation going on out there right now. So with PS, the size is my my virtual size. It includes the code, the data. It also includes shared memory. It includes any memory map files that are pinned down. It does include shared libraries, so shared libraries get counted more than once. If I have several processes using the same DSL, they'll all add up. Even though they're shared, they'll show up within PS as redundant counts. It'll be counted more than once. And then the RSS size is the portion that's actually sitting in memory, physically resident in memory. Mapped devices such as graphic devices are not included in this, but shared memory and shared parts of the program are. Two independent processes that use the same objects and the same code each count valid resident pages as their own resident set. So there again can be overlapping. One of the hard parts is trying to correlate all these numbers between what you see with PS, GMEM usage, and various other metrics. And they don't all always correlate because of the counting of DSO shared objects being counted more than once. Parent PID. So that would be like the shell or something. So my shell is going to fork off the individual processes. In fact, we can see that here. 8849 is the parent PID of my two processes. And 8848 was probably the telnet daemon that was fired off by inetd. But it's running as root, so I can't see it here. So that's just saying who your parent is. We all like to know who our parents are. Any other questions? Also in memory usage, we talked about this a little bit. *R says where my memory is going. And this is all in pages right now. And by the way, I'm in the process of putting together a Irix system tuning guide that's going to have all these metrics documented with samples and stuff like that. So if you go off to my web page, it's my Origin Performance Evaluation Tuning class, OPET. And you can get into tables, and there's a search engine to find anything here. This is the same display as Gross View ARMMC that we were using earlier. So the first field here is the actual physical number of pages on the system. This one has got 2.3 million pages, 16 kbyte pages on the system. So that's total physical memory. It should stay the same all the time. You do have the ability of rebooting and reconfiguring memory smaller or something, but in general you're not going to see that. I would like to see a make part. If I partition the system out into pieces, that should drop down as well, because each OS is going to take a pool of that memory or something. Make part is how I can take a single large OS system and break it into small OSs, each having their own file system, their own root. The second field then is how big the kernel is, and it does include the heap. So the sizes are changing because the space that the kernel needs to keep track of subroutine calls. While I'm in the kernel, I might get interrupted, so I got to keep track of where I am. The next field then is what my users are actually using in pages. And then I've got three fields here that are my file system buffer data. FSCTL is my metadata, my inode and directory block data. On a news server or mail server, those things work with lots of files, so there's lots of inodes there, and you'd like to see FSCTL real big there. But on compute servers, we like to keep it small, because we don't generally open 1 million inodes, with an application run or something like that. Whereas a news server may have a million different news articles that is manipulating within its inodes. So FSCTL is my file system control data. The next one is my delayed write data, or data that I've written into cache but is not flushed to disk yet. It's dirty data. Dirty data is stuff that if the system took a panic, the file system would not accurately reflect the contents of that file anymore. What flushes it from dirty to clean is a sync. Whenever you do the sync system call, it's going to flush dirty off to your disks. The next one then is clean data, FS data. This is data that I've actively used in 2 minutes. Actually, it turns out to be about 100 seconds. There's a systune parameter to control that. But if I have not used the data in 100 seconds by default, it becomes inactive and gets moved into what's called free DAT. And free DAT is data that's old, that I've not reused in 100 seconds, but maybe like on a web server it would be useful because I may hit the page 5 minutes later. Okay. So FS data is actively being used. In 100 seconds it's been referenced. If it hasn't been referenced in 100 seconds, it moves to free DAT. And free DAT is also known as inactive data. Now when I start running short of memory, I'm going to free up the free DAT first. Also, as I'm managing and looking for buffers, I'm going to go through my normal data buffers first before I look through the free buffers. That way I don't have to go through 600,000 buffers to look for something. I only look through the buffers that are active first. Then I go to the inactive buffers. Benchmarkers, by the way, love free DAT. They can run their benchmark, load all their data into memory, and as long as there's no memory shortage, the second time they run it, they don't have to go to disk to get the data. It's already been preloaded. It also distorts timings unlike copies. If I copy the same file multiple times, one time it may be in cache, another time it may not. And you can't get repeatable timings because of that. And the last field then is how many pages are left available. Let's see what we got here. Yeah, I've got 2.3 million here, 2.2 million of them are empty or unused. And again, that one has the bug. If that one gets larger than FizMem, you've hit a bug. You basically have run out of memory. It's a derived metric and they're doing some subtraction in there and it may go negative and then it looks like a super large number. And with gross view, the display would all go green when you hit that threshold. Okay. Now keep in mind also it's vHand's job to keep empty there all the time. So you may be oversubscribing memory and actually having stuff go to swap, but vHand is making sure that there's something empty. On 6.4, the default is to keep 25% of your memory free. Okay? On a 64 gigabyte system, that could be a lot of memory that you're going to intentionally try to waste. In 6.5, they changed things such that we don't try to keep 25% free, we try to keep 100 megabyte free. And I'll get back into that when we talk about some of the systune parameters. So I find star-r an extremely useful tool. And then the other one was sar-r. This is telling me what's left. And my position is I've always got something left. I want to know what's being used and how big the usage is. vHand is always going to ensure that there's free memory. Okay. So sar-r is telling me how many blocks are free in memory. Actually, I think those are in pages. Free mem is in pages, and then the other two are in blocks. And note in this example, free swap is staying at the same allocation, but virtual swap is the one where my allocations are initially occurring. This tells me that I'm allocating memory and never using it because it's surviving on virtual swap and never being pushed to free swap. If that number of vSwap started going down, then I could up the size of my virtual swap. And that third field was new in 6.5. You won't have it in 6.4. So we've got a sample here. Workload was run using gross view. I've got low CPU utilization here. I believe this was a 128 CPU system. Looks like I'm maybe using 10 of them. So this is sar-u data, giving me my user. A little bit of system time on top of it, reads, writes, a few other system calls. Interrupt handlers, looks like I had a little bit of interrupts here, and in fact at the time I had a whole lot of page faults going on. No real page swaps though during this entire interval. I never went to my swap device physically. So low memory CPU utilization. When I look at memory, it looks like about half of my memory is free and it looks like my users are using about half of it. Kernel is pretty small in memory and my cache is staying real low. It looks like this system doesn't have a whole lot of I/O activity because the cache is staying down there. The cache on this system can grow and shrink as needed, unlike Unicos where you hard code the size of the cache and you have to live with that. And I believe that Irix cache works much better than Unicos cache because of this breathing capability. You have to allocate things in contiguous locations. So if there's lots of memory available, I can grow and find an easy contiguous allocation. Whereas if I'm working in a finite resource like Unicos, it gets fragmented very easily. In fact, file system mounting in Unicos will really tear up the performance on a Unicos machine. The number of J90s I've been logged into where NFS was the problem because of auto mounts and fragmentation of cache. When you get in that scenario, you actually get more activity between cache to disk than user to cache. Things actually flip and you're moving more data from cache to disk. Physicals become higher than your logicals. Now, even though there's plenty of memory available, we still have paging going on. It's always going to go on. We have a paging system. And this is just stacking them all, but I can see the majority of my pages are being satisfied out of cache. I don't, yellows are my demand fills. I see a little bit of demand fill page creation. Then I also see the modifies and the copy on writes. Now why they actually added it in here, I don't know, because CPWs and mods really are not part of these three. These are the three that I care about. Demand fill, cache per second, paging text files from the file system, or paging data from the swap device. That's what matters. And we're also seeing TLB activity in this example. Now there is a resizing that occurred here. When it whited out, basically we probably got bigger numbers and we had to resize our scale. So it just shows at the point where I did my resizing or rescaling of my data. No pages swapping at all, and I can see my swap allocations going on, not much change there. And lastly, my network traffic. Looks like we're moving about 200 kbytes out rather than in on this particular system. And is that the last page? See something here. Oh, let me do it again. So I'm just taking RMMC. Now you can actually write a .gross view file to get a default configuration every time you boot it. I'm just saying read what I want from standard in. So I'm asking for the RMMC display, which breaks out my cache pieces. And I'm also asking for it in strip mode. And then I'm also asking for my virtual memory addressing. Probably should have put that in strip mode as well. In fact, let me do that. And then my CPU utilization is the last metric. Okay, so here I can see that I've got large user space. This was my RMMC display, and here it is in strip mode. Kernel is fairly small in this particular situation. So here's my kernel size itself. Here's my metadata, my file system control data, inodes and directory blocks. Here's clean data that I've used in the last 100 seconds. But if I haven't used it in 100 seconds, it moves from clean to free C. And free C was known as inactive data or free DAT. And I have a little bit of problem here. This thing is not refreshing properly as it strips down. Also then see my swap layout showing my memory reservations. We're going to get into a little bit of this. But I got three pieces. I've got memory, I've got swap, and then I've got virtual swap. And these four layers of swap are reserved but not allocated, not reserved or allocated, reserved and allocated. It's basically the combinations of the three. Nothing reserved or allocated. It's at a reserve level, or it's at reserved and allocated. And down here then I can see this particular system's got a lot of system time happening right now, but mostly idle. And what I was going to try to do was see if I can do something that will actually create some problems here. And Netscape is a good candidate. And at the time then, I can see my memory actually grew. And in fact, at the same time, this yellow line, oops, It's easier on a bigger system here. But the events that I just went through, my memory grew, paging kicked in, and it actually pushed my kernel down, but note that the yellow line has gotten bigger now. This is data that was in the cache, the pink portion, that's now been pushed into inactive data. Okay, and that's this free C space right in here. And I'm basically looking like I'm basically out of memory. The only available memory I've got actually has data in it. It just hasn't been actively used. And I don't know, if I were to poke around on the network and try to find different things, we'd be able to create different types of I/O problems. But at this point, I think I'm just going to go on. It's a good time for a break. Are there any questions right now?
How long is the break?
Well, since it's a little bit early, let's go till 1:45. That sound okay? This 5K byte or 5 bytes. So it's not uncommon that all the memory you ask for isn't actually used, because you have to ask in certain chunks and you may not actually use all that space. So the first level is reservation, which is done on the malloc, reserving out of my virtual address space. But then when I actually have to reference the page, it goes from reservation to allocation. And an allocation says the page actually exists, and it will either exist in memory, in page cache, or out on the swap device. Okay. Now, I wish we had workstations in front of us, but the SWP display that I was showing a little bit earlier, this is the gross view man page. And so you can look at the gross view man page, or you can look at the swap man page for a little bit more on this allocation stuff. But we have several pieces. Again, I broke it into 3 pieces. I had real memory, I had my physical swap, and then I had my virtual swap. Okay, so out of real memory, mem is the actual physical memory that's on the system, and then mem-r is the memory that's been available or reserved, that is reserved to processes, including miser. And miser may reserve out of this memory pool and never actually use it. Okay, so that's going to show me how much is actually being used in my physical memory. Then these next 4 are my different levels. F-swap is the amount of physical swap that is neither allocated nor reserved. And then F-swap-R is the physical swap that is not allocated but is reserved. So I may have reservations like mallocs that never actually get touched. This could also indicate memory leaks, where I accidentally keep asking for memory but never release it or something like that. Okay, so F-swap-R then is the amount that's not allocated but is reserved. U-swap is the amount of physical space that is allocated but not reserved. So it's the opposite of this one. And then the last one is the amount of physical swap that is both allocated and reserved in both states. Okay, now if I'm reserving but never allocating, virtual swap comes in handy, because I can reserve on virtual swap but I can't allocate. And the same thing in physical memory. I'm reserving on memory, but there isn't really an allocation scheme there. It's how I'm managing my swap space in terms of saying I'm going to need the space, reserve it for me, or I'm actually using the space, allocate it for me. And in a lot of the Cray markets, the Fortran programs will zero out their array. But maybe they'll ask for a large blank common space. They'll set up this big memory space, and then they'll carve it up into several arrays that may be multi-dimensional, where you've got nested loops and stuff like that, 3-dimensional Fourier transform arrays or something like that, where there may be wasted space in there. So the malloc is just the reservation, and then the actual referencing of the page from the first time on goes from reservation to allocation. Okay. So you can look on the swap man page or gross view man page for a little bit more about that. Now what I was going to try to do here is I've popped up, we're on schedule, so I don't mind getting a little bit behind here. Try to apply a little bit of this stuff. My origin tuning class is where I actually try to apply this stuff, but I've logged into Do out in Egan right now. And I've got somebody running a load on it right now. In fact, Top will tell me who's running. Probably Edward Hall. Looks like just this. I'm not seeing a whole lot. Oh, this is the wrong system, that's why. Did not correlate. So I've got this MP Dyna, somebody named Jeff is running this multi-threaded Dyna 3D, used for car crashes, stuff like that, at a lot of the, everywhere from General Motors and Ford to Lockheed and stuff like that. So I popped up with gross view, my CPU usage, my memory usage in speedometer mode, and then memory usage in user mode, and then lastly what my swap looks like. So here is my actual real physical memory and physical swap added together. And here's my memory reservation and here's my swap reservation. It looks like most of my memory is available. In fact, when I look up here, I cannot see that. Oh, actually, I can see it because it's all gone green. That's that bug that I was talking about before. So I'm not sure what good this is going to do me right now. But what I was going to try to do here is see what happens if I drive a load at the system that's I/O bound, and see what happens here. I basically have a script I call go.bottle that fires off multiple copies of codes that I use. I've got a CPU bound code, memory bound code, and 2 I/O codes. One that does sequential I/O and one that does random I/O. And I'm not going to be able to see anything here. My numbers have all wrapped. I've got the machine so oversubscribed that I can't see anything. My CPU utilization went up a little bit, but what I was trying to do was show cache behaviors. And I'm not going to be able to do that here. We'll have to wait until a particular workload drops down such that I'm back in more realistic numbers. So I'm going to have to defer that at this point. As far as I'm concerned, we're on schedule. The original schedule has us finishing somewhere in process management. So I'd like to get through this by 4:30. What do we got right now? 3. So we got about an hour and a half. We should be able to do that without too much problem here. I don't know if the pace is going too fast for you. Again, a lot of the intent was that the documentation's in the manual. I'm just trying to focus on the big things and trying to apply them where I can. So the next piece is on process management. We talked about memory management a little bit. Now we're talking about process management. And we're going to talk about the process life cycle, how a process is created, how it executes, interruption, and termination. Talk about CPU scheduling and something called the run queue. Anything that needs a CPU is on the run queue, ready to run, or else running, connected to a CPU. And it's priority based. Context switching is how we time slice the CPUs. And there's going to be a little bit on accounting. The kernel has to keep track of how much execution time a process has consumed, both in user mode and in kernel mode, known as system mode. So we're going to see some of this data, but the accounting data is where a lot of this eventually comes up. But with the PS command, I'm able to see stuff in terms of how long it's been running. And when a process terminates, a lot of that accounting data from PS and a few other structures gets written into an accounting file, which I can then view later and see how long did my program take. We've got to track a little bit about the memory usage and consult the memory subsystem to allocate and deallocate main memory when needed. Exception handling, how to handle, for example, divides by zeros or addresses that are outside your allowable address range. And there's going to be a little bit about I/O processing. Now the format for our executables is different on Irix than Unicos. We have what's called an ELF, executable file, executable load file. Basically a program is the executing file residing in a file system. The compiler is going to build me some sort of executable called a.out. A.out standing for absolute binary .out. In my personal finance, this is like checks to cache. So all A.out formats use the format called extendable linking format. And we're going to see a little bit about that structure. Let's see. And Yeah, a single-threaded program loading in memory may have multiple text and data segments, but only one stack segment. It's multiple text if they're sharing shared text. For example, all the shells on the system may be shared text executing the same executable binary sitting out there, possibly in the file system or possibly in cache. And you can't really share data segments, but there may be shared memory data segments, things like that. And then the text segments are not writable by the program. If other processes are executing the same A.out, they may share the same text segments, but they can't change anything in that text portion. And what we're looking at here then is showing a linked view and an executable view. The loader is just going to build this thing that has what's called the ELF header, a program header, and it's got sections for all the subroutines, and then there's a section header table at the end. Whereas the executable portion, they're just trying to show that it's got the same structures, but now it's been broken into segments. And for those that are interested in tuning, there's something called CORD, C-O-R-D. Basically, you run your application and you collect some reference data, and then CORD can rearrange the subroutines to put them in localities such that they're on the same page. So if I know that I've got 3 subroutines that I'm always referencing, CORD is going to shuffle them and put them such that they're on the same physical page, and then I don't have to take as many TLB misses on that sort of thing. But you got to run the application first to collect a CORD feedback file in order to run this CORD utility. ELF dump is the main thing that dumps and pulls apart this binary or executable, this A.out. With ELF dump, you can find out what DSOs does it use, what are the subroutines within it, things of that nature. Let's see. Got a couple examples here that are just using a -F and a -H option on there. And I was talking to the developer of the manual just yesterday about the importance of this, and he was thinking about taking it out here. But basically what we've got now is this is a column type of thing. So we've got the program header, the section header, and then the ELF header, the ELF header itself. And this is just trying to show the offset pointing to where the program header table starts, where the section header starts, and then where the actual ELF header stops. So these are just pointers into the binary where that particular piece of the executable begins. There's a lot of things on here that I don't pay any attention to. It is showing that it's a 32-bit binary as well, and this address right here happens to be the start execution point of your program. So with ELF, it's basically pulling apart your executable and saying what's in it, giving you some address offsets. Everything here is hex. X in front of it, 0x indicates hex. Okay. And by the way, the file command can also tell you what kind of binary you have. Oops. So for example, I did a file on binls, and I find out that it is an ELF binary. There are older binaries that are no longer supported. They're called COFF, C-O-F-F, and they aren't supported anymore. So ELF is the primary executable format. This is saying that it's an N32, it's a 32-bit for new CPU architectures, meaning that it understands an R10K chip and stuff like that. And it's MIPS 3 instruction set, dynamic executable MIPS program version 1. But you can find out a little bit about how it was compiled from the file command, but then ELF dump would be able to pull the binary apart a little bit more. And the next page is just then showing that the executable, the address here, they did an ELF dump -H on the catalog. Over on the right, you can see all the segments or pieces of the program. In particular, here's our executable portion, .text. And this is my entry address, 130, saying I'm going to go into this particular address alignment to begin executing my .text portion of the program. But I myself don't have a whole lot of relevance to those two pages other than they're just trying to explain how the binary is put together and what ELF format is like. But if you do need to, ELF dump is extremely useful to know what kind of libraries you're using, what DSOs you're using, stuff like that. So a process is the execution of a program or executable file stored in the file system. It has what they've marked in here is 2 pieces. Really, we've got 3 pieces. We're looking at 2 processes. The text portion, which could be shared. For example, all the people logged into the system are going to execute the same shell. They're going to run off the same executable. And the purpose for shared executables was to save memory. We've got a lot more memory in these systems nowadays, and it becomes a trade-off because now we keep going to the same node to get that dynamic shared object. So imagine a 256 CPU system, and all CPUs keep going to a matrix multiply routine, and you have to go across your node architecture to get to that. This is why everyone's going to stress origin machines are cache-based, and you really want to fit everything into cache to take advantage of this machine. And again, the text portion is shared, but it's read-only. We can't have another process modify it. We can't ourselves modify it. The second portion then is my data portion, and this is private to my process, but it is read-write. And what they're trying to show here is that this text portion cannot change the data or stack of a different process. Okay, it's unique to my process. So when I define a program subroutine, at the top of the subroutine I may define some variables, global or local. Those are going to go into the data portion. Okay, so local and global variables are going to possibly be defined in the data portion, but when I do a subroutine call, local variables get pushed off onto the stack so that when I come back from my subroutine I know what my environment was before I went off on the subroutine call. And it's also trying to show now the data portion read-write. It's growing from low address high, and then we've got something called the heap or the BSS space that's growing from the high address down. So we've got 2 things growing towards the center. And the BSS and heap space is the area I was talking about that has often got wasted space in it, where I may malloc a large BSS space and then carve my data arrays into that BSS space but not use all of it. And when I do a memory growth and ask for sbreak or mallocs, it's the data portion that I'm growing. Okay. And then the third piece is the stack, and the stack is used just by the operating system. It has no real user data in it. Again, it's basically saving off where was I and what do I need to know when I come back from a jump. So any sort of register environments, any sort of variables I have within that subroutine gets saved in the stack. If you multi-thread, each thread has address on the stack. So as you start getting wider and wider in thread widths, if I go 128 CPUs wide in an application, I'm going to have a larger stack. And there are limits, different limits for text, data, and stack. They have 3 different sets of limits for those. It's not uncommon when I start multi-threading to have to start upping the stack limits. And a word of warning, in the Irix world, you have to check your syslog a lot more than you do in Unicos, because you may see errors and messages in the syslog that did not come back to your program's output. And stack limit exceeded is one of those. So Unix type person, syslog is pretty big. You just got to get used to checking it more as an end user, because there are messages there that you won't see elsewhere. Now there's one other space, I guess it's just showing the stack is growing from a high address down, but again those are 3 different images, 3 different pieces of the program. And the last piece is showing us that there's something called the U area. Now the U area is pretty much gone in 6.5. U area was kind of an older term for, and we had it in Unicos as well. It was called user.h. And in the older days, basically it was attached to our process. So we had our a.out, and on Unicos at the lower addresses we had this user.h. And in there we would keep track of files that got opened, accounting statistics, bytes moved for I/O, all the system type of structures that were associated with the process. Well, in 6.5 this user.h is gone, and basically this got broken up into several pieces that are now in the kernel heap. So now instead of saying it's out of user space, it's really out of kernel heap space. And it's called a lightweight thread structure, a UT_structure is where a lot of that information went to that was in user.h. So older Unixes will refer to user.h, but both Unicos and Irix 6.5 have eliminated that and gone into what's more of a thread structure. And they're basically breaking a big structure into several pieces. And then when they lock a structure, they don't have this big structure locked, but multiple threads could be manipulating through those individual lightweight threads a lot more conveniently without a lock on the whole thing. single threading or serializing your data or your program going through the lock. So they will still refer to that thing as a U area, but it's really called a lightweight thread area now, and it's within the kernel now instead of within the user space. And also then the process has to have a page table, and that is also within the kernel. And gmem usage can show the page table, but the U area is part of the heap now. And the kernel asks for space out of the heap when it needs it. So the text portion is my executable series of bytes, read-only, shareable. Data portion, memory region is private to the individual process, can be read or written. By the way, if you exceed the limits on your data segment, you get a segmentation error, like a bus error. It's called a segmentation fault. And a segmentation fault means I tried to address outside my legal area of what I've been told that I have. It's kind of like a operand range error within a Unicode type of interface. And the data portion consists of two parts: the initialized area, which is called the global and local variables of the program, and then the uninitialized area referred to as the BSS space or the heap. And BSS comes more from a Fortran environment. And heap, the term heap kind of came about maybe about 10 years ago when we started managing it as a heap rather than a Fortran method of managing this memory space. There used to be in COAS something called memory. You'd call this memory library call, which would then allow you to grow your memory space in this blank common area. And they rewrote that in mid-80s and called it heap. In terms of memory management, I was talking to somebody during break, the oldest program I've seen, I date pre-1960. And basically in pre-1960, what we were doing was look at the data and then hard code the array. So they'd have a preprocessor look at the size of the data set and then say, oh, this thing's going to be such and such a size. Then they build a main for the Fortran program. This was at ARCO, for example, a seismic program. And they build the main and then compile, actually hard link in the size of that array. Okay, which means it's static. I can't change it once I've done that compile and link situation. The second thing that came along, really to me, came about with cyber CDCs and stuff like that, and that was call memory, which we implemented in COAS. And call memory was a way of managing the BSS space and to grow that. And nowadays, we then get into heap, which is more Fortran based, or Malix, which is more of a C-based type of thing. And a malloc is simply a different way, a C interface to ask me to grow the heap. It's really a matter of the programming environment you're used to working to, Fortran versus C. But there are still programs out there that don't do any memory management at all. They just look at the data set and build the program for that size. Nobody wants to rewrite them because the person that wrote it's retired, right? Not my problem. That's what everyone will say. And people are, in general, sloppy about their memory use. And then the stack is used to hold locally allocated variables and parameters that are passed into your functions. So when I make a subroutine call, parameters are passed through that stack, also referred to as a frame on the stack. Each subroutine basically has a frame on the stack for that subroutine call. And the U area is used by the kernel for controlling the user process, keeps priorities, things that don't fit in the process table. Basically all the attributes about the process that doesn't belong in the proc table. And it's not addressable by the user. You can't get to it directly, but you can get to it through /proc. /proc is a file system interface to see what a.out looks like. So you can reference your own user area space through the /proc interface. And lastly then was associated with the process was the page table, used to translate the virtual to physical, managed by the kernel, and it's used to load the TLB. Each process has its own user area. Again, not addressable by the user program. I can't modify it or anything. The kernel manages that. But I can read it through /proc. So let's see, some of the attributes is maybe in main memory or paged out to swap if memory becomes scarce. I'm not sure if it's swapped out anymore. It's all part of the kernel heap now. I'm not sure that that's valid with the latest release. You might put a question mark about that. It's accessible only to the kernel, and it resides in the kernel memory space. It resides in the kernel heap. And that's why I don't think it's going to get paged out to the swap device. But again, I'm not positive. And it holds all information relevant to the process environment. One of the key things there is every time I open up a file, I've got an open file table in this user area, and every file I open is going to add pointers, file descriptor pointers, in that user.h structure. So it holds information like the user ID, the real and effective IDs, the current directory you're in, keeps track of all your open files. There's information on signals. There's shared memory segment information. A lot of the accounting information, like characters that I've asked to move, bytes moved and stuff like that, are in here. However, things like priorities and stuff are actually in the process table, not in user.h or the user area. So again, that's kind of an older term. What they're really calling it now is a lightweight thread, or a thread structure, user thread. The next slide is just breaking out my stack portion, and we're looking at a subroutine call. Each subroutine basically is what they call a frame. So we start off at frame 0, and as I keep jumping in my program, for example, from main, I may jump into another subroutine, and every time I jump off to a function, I have to save my environment from the previous function off into the stack. So every subroutine, when you jump out of it, has a frame set up that sets up parameters to main, or parameters that are being passed in, so you know the argument count and the pointer to where the arguments are. A return address to know where to come back to in your subroutine you jump from. A link back to the previous frame, and then the variables that were saved off in that subroutine that were local, unique just to that subroutine, not the global ones. And then if main jumps off to function 1, everything in main's environment has to be saved off in this frame. And then when I'm in function 1 and jump off to function 2, I'm going to have to dump off function 1's environment here, and so forth. So as I increase these subroutines deep, as I keep jumping deeper and deeper, I'm adding on to this stack. And then as I return back out of them, I'm pulling back off the stack to return to where I was before. And it's all managed by the libraries, and really the libraries more than anything. It's automatically created and dynamically sized. There is a limit to the stack, and it's not uncommon when you start multi-threading to hit that limit. Because again, if you got 128 threads, that main function is going to have 128 frames, one for each thread. Logical stack frames are pushed onto the stack when a function is called and popped off the stack when returning. The stack pointer indicates the current position in the stack. The stack frame then contains parameters passed to the function, local variables, things like that. And the kernel grows the stack as needed. There are a lot of tools that monitor the stack. For example, there's a program called ssrun. And you basically are going to look at the stack and statistically, periodically check the stack and see what program names or function names you have in there. And then you can determine how often am I calling this function based upon how often it appears in the stack. So ssrun is an example of a program that can view the statistics of this stack and periodically poll it and see what subroutine names show up in there. So at system call or exception, the kernel is going to switch attention from user to kernel space. We always call that an exchange in the Cray world. That's really just a software switch or a context switch into the kernel space. So they got an example here where they've got the program showing the text, the data, the stack, or the BSS space, the heap, the stack. And then there is a kernel stack as well, because I may, for example, get interrupted, make a system call into the kernel to do I/O, and then get an exception during that time. Originally, Unicos only had one level deep of interruptions, but the newer ones, we can actually take an interrupt while we're in the kernel. Okay, so that's what we're saying here is if I'm in the kernel and take another interrupt, I'm going to have a kernel stack so that I can go off, service an interrupt, and then come back to where I was in the kernel to finish off whatever work I was doing. So it's a second level of interrupts. And in fact, that second interrupt level may be a software exception saying, I can't find the address to my page table. Okay, so the program may say, I can't find an address in my TOB and ask the kernel for it. And the kernel says, well, I can't find the page table, so I've got to take a miss and cause a software exception and interrupt to say, find the page table entry for me. So the kernel stack contains stack frames for functions executing in kernel mode, system mode. If I'm in the middle of a read call and a TLB miss comes along on me, I may get interrupted. Whatever I was doing within that one function is going to get saved off, and then I can return back to it. There have been problems in the past of leaks in here as well, where I may allocate memory out of the kernel heap but forget to release it or something. A lot of 6.4 systems had that problem. And a lot of this memory is allocated out of what's called the zone allocator. And in 6.4, you actually have zone allocation metrics, sar-h. Oh, this is 6.5. Let me get 6.4 here. They took it out in 6.5 because it's a hot path. And we don't want to over-instrument these systems. Though I have to admit, Irix is more instrumented than Unicos. There's a lot more metrics that are available and a lot more tools for me to look at the system than Unicos. So I was going to do a sar-h on a 6.4 system. Oops. And over here on the right then, my zone allocator. So here's the amount of heap memory that my kernel's keeping track of all these subroutines, how much is being used, how much is unused, how many allocations out of the heap I'm making, how many frees I'm making. Hopefully I'm freeing up stuff when I'm done with it. And then for the zone allocator, also how much memory is allocated for the zone. The zone allocator is allocating memory round robin among all the nodes. For example, file system buffer cache, whereas the heap is primarily on CPU 0. And then lastly, we've got allocs and frees. Now these were taken away in 6.5 because that's a hot path in terms of asking for memory out of the zone allocator. So they took that away to reduce the overhead of going through that particular portion of the program. And again, displaying the process memory was GMEM usage. We kind of already saw that. Looking at a program here called SH. And again, GMEM usage is going to combine all SHs on the system into one report. And then you can do a page down to navigate to each individual process. So it's summing all the shells on the system. And I've got my read-write data, read only. There's a text portion that's libc, data portion for libc. I've got text and data portion for a program called RLD. And then here's my actual shell, text portion, data portion, and sbreak portion that's unused. So here's part of the memory mallocs that the shell has asked for, but never actually used yet. It's got extra headroom there. And then here's my software stack. And then I've got the kernel stack visible here and also the page table entries. PTE is your page table entries. So your page table has one entry per page of your process. And we were able to look at this by drilling down with the region viewer into the actual process. And then we could zap it, color it everything to pink, and then we'd be able to see as it hits a page whether it goes valid or not, whether it's sitting out on swap, some of those sorts of information. So the region viewers was actually visualizing this for us, this PTE area. Now what we're trying to show here is the fact that I've got a multi-threaded system. Each CPU has a private data area in main memory. And there's some newer terminology that came about in the last 5 years called a thread rather than a process. So when a process is created, there's something now called a thread structure dynamically allocated in the kernel, which is used to control the process. And it controls things like status of signal, CPU scheduling, current system call. A lot of that stuff was in user.h before. It's now in the kernel in what's called UT_ structure, a user thread structure. And then we've actually got the /proc structure, the process table, dynamically allocated in the kernel. It keeps track of who the parent is, the child is. There are run queue links through the process table, things of that sort. So again, we got three pieces to the program as far as the kernel controlling it. The addressable area of the program, the thread structure, which used to be known as user.h, and then the actual process table structures themselves. And a ps command is what prints out the proc structure. So we're looking at here where we've got two CPUs. We're firing off process A and process B, create a private data area for the process, create a thread structure for the process, and then create a process entry for the structure. And the process entry is then going to point to the actual location of where this process sits out in memory. And then 4 was the user area and the page tables. Part of the user process can't be directly addressed by the user, and the U area is primarily used to save the context of the process. Okay, when I do a process switch, that's just a CPU switch. I'm taking one process and taking it out of the CPU and letting somebody else use the CPU for that time period. Just seeing nothing else of interest to me. We also talked earlier about process credentials. When a process starts, we have to create the credentials. CRED structure within the kernel. And in that structure, we're basically keeping track of who we are, the user, the group. Real is what I logged in as. Effective is what I SU'd to, or set UID type of operation, where I've got a binary out there that may be executed as root with a set UID bit set. And then also security information, what's called a mandatory access control, MAC labels, and privilege sets, what am I privileged to do, and any sort of supplemental groups that I may be a part of. So when you log in, a majority of this information is obtained by ITSI password. And it talks a little bit about the effective user IDs, where you can do a set UID or set group ID on a program. And then I could run somebody else's program and gain their permissions while running it. And a lot of that's going away these days due to security leaks. Having set UID programs is often discouraged out at sites because of the abuse of the privileges that they may obtain. And then mandatory access control label is the security label for the process. I like that. It specifies the trustworthiness of the process owner and the level of information the owner is authorized to read or write. Irix has got two separate source trees. There's standard Irix and then there's trusted Irix. And trusted Irix in the source tree is known as Trix, T-R-I-X. So you may see Irix-Trix or something like that. That's a separate source tree, and that was certified, I think it's 6.2, but 6.4 and 6.5 and newer ones have not gone through the certification process. And they're not as certified at a high level as Unicos.
Remember zip giving root privileges and
ZUP is, yeah.
Have anything somewhere on
We're using sudo. I don't know why they chose sudo over ZUP, but all of our systems in Egan, SUDU. Okay. Now with ZUP, it just checks to see if I'm valid. With sudo, there's actually a second level of password checking. But it's the same password that I broke into the system with. So if I broke into the system with a stolen password, I can reuse it and get into sudo type of things.
I got a copy of ZUP there.
Yeah. And like I say, I don't know why they went with sudo over ZUP. Sudo seems to be a little bit more common. SUDO. And it just seems more common in the Irix world.
Who does the certification?
Certification of what?
You talked about the security certification.
Uh-huh.
Who actually?
Well, the DoD is the one that does the certification, and we try to help them. And they went through the same process as we did in Unicos several years ago. But then once we got a validated one, we don't go through that process for each update release. So we say we had the basic functionality there, but it's not certified anymore because nobody's tested it and said that it's actually performing as specified and stuff. So the features are there. And again, Irix is not at the same trusted level as Unicos is, and we'll get into that in a later section. And it's the login process, basically, that's doing the certification of anybody logging into the system. Now in this process table, we may have several chains through the process table. So there's linked lists going through this process table. So they're just trying to show an entire process table here, and one of the linked lists through there is the process group. So everything that is, for example, under my shell is going to have the same process group ID. And then I could kill the entire process group, for example, if I needed to. So there's one linked list that connects all the processes that are in the same group. We've got another linked list going through the run queue that's my run queue itself in priority order. So for each process or thread on there, I can see what's ready to run in a particular order. Now it doesn't really show it here, but in 6.5 they have run queue per CPU. And par little r, if you put a little r on, will actually show you what the run queue length looks like for each CPU. R, not P. And again, Irix view can actually plot that sort of thing. Irix view will give you a GUI and show you context switching on a per CPU basis. It'll visualize the par-r report. So each CPU has its own local run queue. We do this for affinity. That way if my CPU goes free, I look for other threads or other processes that were on that CPU. That way anything that it was using will hopefully still be in my local memory and maybe in my cache. If I don't find it on my local run queue, then I go off to another CPU and look at its run queue. And I always try a neighbor first. So there is a priority scheme in here, but the run queue is split out on a per CPU basis. And par-r will print out what the run queue looks like on a per CPU basis. So you can see the actual PIDs and stuff like that that are on the run queue for each CPU and what their priorities are like. There's another linked list there for things that are running. These are ones that are actually connected to a CPU, actively executing. Then there's another linked list through the process table for things that are sleeping. This could be something as simple as the sleep process, or it could be something like I did I/O, the I/O is not done yet, I did it synchronously so I get put to sleep while I'm waiting for the I/O to finish. And that's probably the most common reason to be on the sleep queue, so to speak, is I'm waiting for some sort of I/O event. And also something called a process family, my parent and all the children underneath it. We'll come back to that a little bit later. But my parent process might be my login shell, and then all processes I fork off are part of that same process family. And another common name for this might be in a session. A job ID was the Unicode term for it, but POSIX came along and said, we don't call these things jobs, that's too IBM-ish, we're going to call them sessions. And a session ID or a job ID are essentially the same thing. And in the SGI world, when we get into clusters, a cluster or an array being multiple mainframes put together as a single system image, when I send work off to a cluster, there's a program called the Array Service Daemon, ArrayD, that negotiates the same job ID or session ID on all nodes of that cluster. So when I consolidate the amount of work that I did, I can consolidate it down by this process family across hardware boundaries, across OS boundaries. For example, MPI, Message Passing Interface. It's a programming language to spread your work across mainframes. And in that scenario, the MPI job, you'd want to have the same handle on every CPUs, on every OSs within the configuration that you've got. And this is implemented in Unicode as well. And for example, in SV1, the bigger systems are clusters. So they got to have the array daemon running to negotiate a common session ID or family name for all machines within that cluster configuration. And when you configure array D, you specify which mainframes, which host names are going to be part of that array. So in the Cray world, we called it a job ID, and JSTAT printed it out. But lately, it's called a session ID, and there's no tool in Irix to print out the session table. And this is just trying to show that when I create my process, the thread has a text segment, a data segment, the stack segment, and may have some shared memory. So it divides the address space of the process into segments or regions. And with GMEM usage, we were going into the region viewer to look at those segments. Several processes may execute the same program and like multiple users of the same shell. Therefore, it makes sense for them to share the same copy of the same text region. Anyway. And then the kernel's region tables. Every time I create a process, I've got a P region that may point to a data segment and a stack segment for each of the processes. So we've got private regions and we've got shared regions, both data, stack, or in this case, text and shared. Yeah, private and shared. So this region table allocates an entry in the table for each active region. They keep track of where each region resides in physical memory. It's process-independent attributes. Each process has a per-process region table, where each entry is referred to as a P region. And that's kind of what we were looking at with GMEM usage. And the P region entry then has a pointer to the region table, which points to where the region resides in physical memory. Lots of pointers. The P regions are maintained in two separate lists. One is private and the other is shared. In this example now they've got two different processes and it looks like some of them are sharing. For example, A and B are probably the same process name because they're text segments. We've got the P regions pointing to the same text segment portion. Okay. And A and B have their own data segment and their own stack segment, but it also looks like they're using shared memory to communicate between the two processes. Okay, so those are the shared portions. So what they're talking about here, shared memory, reduction in physical memory requirements without taking up large memory footprints, less kernel paging because there's only one copy in memory, and then process start time is reduced if the program's already in memory. A lot of this stuff may be sitting in cache too. I'm going to show you this a little bit tomorrow. Let's see what it looks like here. New in 6.5 is a command called buffview. And I sure wish I had it on Unicode. So the number of sites I've been to where buffview would have saved me a week of analysis time to tell me what was going on. But buffview tells me what's in my cache. And for example, I do have RLD sitting in cache. Here's a shared library that's sitting in cache. This is the kernel cache space that RMMC was showing growing. And this particular system has 125,000 buffers that I can describe data with. And I can see that, for example, these system ones are my inode data. Each file system, these are each separate file systems. Okay? And for example, some of them you'll actually see the name of the file system. Others you just see the dev disk name. So these are typically inodes and directory blocks sitting in here, and we've got 1, 2, 3, 4, at least 5,000 sitting there just for my metadata. But in the meantime, I've still got other things in here like this libc that's been sitting in my file system buffer cache. So it's preloaded, and it's shared objects. So if everybody's using it, it'll sit there, and I won't have to go to disk to get it. Now we're going to come back to buffview tomorrow. But it will tell me what's actually sitting in memory that I've preloaded. Then I don't have to go to disk to get it. Okay, the time slicing is for CPU context switching. Irix is a multi-processing environment. Each CPU can execute only one thing at a given time. It's ironic the number of people that log into the system and think the entire system's theirs and don't realize that they have to share it with other people. So they'll log in and try to take all of memory, all the CPUs, and then they get poor performance because other people are competing for those same resources. Okay. This is not like a T3D. With the T3D, I'm guaranteed and dedicated streaming through those resources. With Irix, I've got to share them. So this is done by time slicing. As I mentioned earlier, we have clock ticks to do that. I think this is where we're going to talk about slice size. So the kernel gives the illusion that it's dedicated to you by time slicing the CPU among different processes. And a process will receive a short burst of CPU attention called a time slice. And time slices are different between Irix and Unicode. In Unicode, it's basically a 10 millisecond time slice. In Irix, you can adjust what the time slice is. You can slow it down. So to a user, it looks like multiple processes are all executing simultaneously, but in reality, one process is at a time, short bursts, and everyone is time slicing through this resource. Now, when these CPUs were small and stuff, time slicing wasn't so bad. But now that we're on cache-based machines, every time I time slice, my caches, primary and secondary, have to be managed. And again, we went through the same thing when we increased our vector register sizes on the T90 product line. It now took more overhead to dump all the CPU context register stuff off into memory to save it off. Okay, let's see. So on a multi-CPU system, multiple processes can be executing simultaneously in the various CPUs. So each process runs in its own address space and behaves like all the machine resources are it. Just going through the drawing here, a CPU is executing in a user process is said to be in user mode. So we're executing libraries, what we compiled, or standard Unix utilities like ls or pwd. At some point, we have to go into the kernel. So the user process enters the kernel mode. Commonly, for example, when I make a system call, if I do a read or write or something like that, if I get time of day or uname, that results in a transfer of control to kernel code, and I'm in kernel mode or system mode. Some of the others mentioned here, I could generate an exception fault such as divide by zero or page miss. I can get interrupt occurring like from a terminal, a control C. And again, the clock interrupt is always interrupting me every 10 milliseconds. Every 10 milliseconds, I might get a minor clock interrupt. So every time I go into kernel mode, the context of the process is saved before entering the kernel so that I know where to come back to when I'm done. And then when the CPU leaves the process and enters the kernel, it's executing in the kernel on behalf of the user. It's said to be in system mode or kernel mode. And SAR was tracking that information. How much time was I spent in kernel mode? In kernel mode, by the way, the CPU is authorized to execute privileged instructions. Just like in Unicode, I can initiate I/O commands that are now controlled by the kernel to make sure that all the housekeeping was done before I said initiate that I/O. And a user process cannot access the kernel space. Traditionally, we were able to get to the kernel space through dev kmem. But dev kmem is considered a security leak, and they're kind of getting rid of it. And nowadays, we're getting information through system call interfaces. There's a system call named sysmp. And sysmp, for example, is instead of reading kmem for SAR data, sysmp is how I get that sort of SAR type of data. And then I can control the interface through these system calls versus a wide open read kernel interface like dev kmem. And the T3E, for example, doesn't have dev kmem anymore. We switched to unique system calls within Unicode as well. And then when the kernel has completed execution on behalf of the user, it restores the context of the process and returns control to the process at the location it previously was interrupted. Now there may have been other codes that ran in the meantime. For example, I could have done an I/O system call, gone to sleep, somebody else got onto my CPU and ran, and then I eventually got control back because my I/O was done. Now I have to wait to get reconnected to the CPU. I have to get priority to connect to the CPU before I can go on. So a system call is the mechanism that the user asks the kernel to do work for it. It's like asking your mom to clean the bedroom or something. Some of the most common system calls, open, reads, writes, close, chmod, chown, kill, are very common and normal and acceptable. The computer's no good without doing I/O. You got to have something in terms of system calls. But there are a couple of bad system calls. Unfortunately, we don't track them historically on Irix. In Unicode, there's a SAR-T report that will tell you historically what calls were being called. But in Irix, the only thing you can do is be on the system at the time of your high system call events. But the bad ones, sync. Sync flushes your cache to disk. In fact, anybody notice, and if you've been around a while, when we went from Unicode 7.0 to 8.0, the df command slowed down. Because df has to sync all the buffers to disk in order to get an accurate report. Because without it, the df would not be accurate. We'd have data sitting in cache that hasn't flushed to disk yet, and then things like data migration were not accurately running. So the df command in Unicode does a sync every time, whereas in Irix it does not. Okay. And unfortunately in Unicode, the data collector for NQE is doing a sync every 15 seconds. So every 15 seconds you're flushing your file system buffer cache to disk, no matter what the state is. Another bad system call, sbreak, asking for memory. Other bad ones, things like uname. Ran an application that was doing uname 10 times a second. System name doesn't change that often. There are better ways of doing that. Get time of day. And there is a big one, a real big one that is really dominating both the Cray and the SGI markets. In SGI it's called SGI NAP. In the Cray world it's called resched. And this is how, in a multi-threaded situation, I give up my CPU so that somebody else can use it. And I've literally been on like EPFL, had I think it was a 32 CPU T90. 50% system time, and all that time was doing resched system calls. This is how I synchronized multi-threaded applications. It's like playing phone tag. So if I say go 32 threads wide, that's 32 people on a party line, all trying to talk to each other, talking to somebody else saying, have you done your portion of your work yet? So if I get a busy signal, if I dial into that party line and somebody else is talking on it, I can't do anything. I can't check to see if they're done, so I relinquish the CPU and give it back with an SGI NAP, which allows somebody else to use it. Now, if nobody else is on the system to use it, it comes right back to me and I release it again. And in the Cray world, the frequency of these occurring was something called MP hold time. It says, how long do I hold the CPU if I can't get onto that party line before I actually release the CPU with the system call? So if you had high system time in Unicode due to reskeds, you'd then increase your hold time and hold it longer before you made the system call, reducing the number of calls that you're making per second type of thing. In the SGI world, it's called MP hold time, or I'm sorry, MP block time. And it's the exact same type of mechanism. How long do I hold the CPU before I release it and let somebody else use it? And if there's nobody else there to use it and my block time is real short, the CPU is going to come right back to me and then I'm going to release it again, and I basically thrash on that system call. And both Crays and Irix machines, this can account for 30 to 50% of your system resources being consumed, just trying to synchronize. Okay? And to me, this is like playing phone tag with somebody. You're trying to talk to them to see if they got their work done, but they're not on the other side of the phone because they're busy, off in some other office, and you leave a message on their voice answering machine and then try to get back to them later, and you keep trying and pulling them saying, are you done, are you done, are you done? Okay. This other method is saying, I'm not going to keep calling you, I'm just going to hang up on you. Let somebody else use the resource. So in this example, a user program has to issue a system call by specifying the name of the specific call with an attached list of arguments. And man pages document all these system calls. You can do a man on SGI NAP or a man on resched for Unicos. And for every possible system call, there's a unique library routine that processes it within the kernel. Basically, the control is passed to this library routine, which sets up the call into the kernel. And as far as the kernel is concerned, every system call is an integer number. So when I make the call, I basically set up the call number, and then the kernel picks that up and indexes into a table to figure out which system call I made. It is not by system call name, it's by an offset number. And occasionally you may, for example, have old system calls and new system calls. Like in Unicos, we had stat, and then we rewrote it and called the old one ostat, so that applications that were compiled on a previous operating system would still be able to get to those system calls. But then 2 releases later, they would get rid of that old system call, and now applications that were compiled 2 releases ago won't run on the system because the system call doesn't exist anymore. And you get what are called illegal system calls. So the library routine invokes an instruction that changes the execution mode to kernel mode, creating a software exception to the kernel, passing control to the kernel. Kernel looks at that integer to figure out what the desired system call is, pops up the system call handling routine like a read or write, and all that is done by looking up in what's called the sysint table, which is the same thing we have on Unicos. So the sysint table is a table offset where the system call number is the slot position within that sysint table. So it goes into sysint to find the actual address in memory where the system call handler is. Then passes control to the system call, and the system call will execute. Now, some system calls can't have multiple CPUs in them at the same time. Some can. For example, uname. I don't have a problem with all the CPUs asking uname because that's a read-only mechanism. But if I'm trying to manipulate something like a read, I'm going to have to lock structures. I cannot have multiple CPUs changing a kernel structure at the same time. So we get into locking mechanisms, and Unicode does the same thing. Back in Unicode 7.0, it was one CPU in the kernel at a time and one lock to get into the kernel. And then we went into a multi-threaded kernel where we had locks down by the structures rather than just the exchange mechanism. So now you could have multiple CPUs in the kernel doing things as long as they weren't in the same system call manipulating the same table, like a disk structure table or something like that. So this allows, particularly as we get into more and more CPU systems, it allows all the CPUs to be doing system type work. And we're basically getting the granularity of these locks tighter and tighter. And by the way, those locks may result in a sleep. And if you do a PS-L, and this is kind of nice, it's still on this system. Traditionally, the wait chan event is specifying what lock you're spinning on waiting for. And I've instrumented Irix, or Irix on this system has got lock names rather than lock addresses. And if anybody gets into that, you can talk to me. There's a configuration change to actually see the name of the subroutine we're sleeping on. And KT wait is a kernel thread wait, just waiting on a sleep. I was looking to see if we have any IO waits. It'll show just a raw address if it's a terminal driver, like the shells and stuff that are waiting just on terminal interrupts. And here, for example, is a process sleeping, proc wait, doing a sleep system or wait system call. Let's see. If I go off on my workstation, it won't have that. Instead, it will be all wait chan addresses. So whenever I make a call into the kernel, if the logic that I'm asking for help from is busy from some other CPU, a lock is set, and I will be put to sleep waiting on that lock to be freed up. And that's what the wait chan event is what event am I waiting to clear up before I can go into that portion of the kernel. And I'm in the process right now trying to document all these different locks. The two bad ones are BIO lock and buff lock. BIO being direct IO and buff being file system buffer cache IO. So when you get an IO bound system, you'll see those two locks quite a bit. So eventually the system call gets finished, the system call executes, we free up on all of our locks and are able to get the work done. And then when finished with the request, for example, a read, the system call handler returns to the kernel code from which it was called. And most of these system calls, if you have a lock that you sit on, it's called a blocked system call. Blocked means I'm waiting, I'm sleeping, waiting for some sort of lock to free up. And then the kernel returns the user process control back to the library routine, which originally passed control to the kernel. And then the library routine returns control back to the user program where they actually made the read or write or printf or whatever it was. Now, creation of a process, there are basically two ways of creating processes these days. One is the old fork, and one is what's called sproc. And sproc is not Unicode specific, but Irix specific. sproc is unique to Irix and SGI. And sproc is how we create multi-threaded process entries. S stands for shared. So in a multi-threaded situation, if I create 16 threads, they're all going to do a matrix multiply on a stream of data, I would be using sproc to do that. Now there's been a newer standard put on top of this saying all the different vendors are implementing multi-threading in different ways. So there's now a library interface on top of that called pthreads. And pthreads is a POSIX compliant library interface to do multi-threading. And in 6.4, for example, pthread calls would still call sproc system call to create the process, except with the sproc interface, they're all shareable. All the processes are able to address each other's memory areas and stuff like that, so that I can have a large data array that I'm going to run through a matrix multiply or something, and all the different threads can take a piece of that thing and process them in parallel. So context of a process. The context of a process is its current state. The state is basically a snapshot of its text and data areas. It also has to have information about the user and kernel stacks, the thread structure, and the proc structure. And then there's the user area, region structures, and then the internal structures like the CPU register contents, and various other kernel structures that have to be help tie this process together to the system. And again, the kernel's text and global data areas are shared by all processes and not considered part of the individual process context. Let's see. And then context switching is where we basically swap or time slice something in and out of the CPU. So we're looking at here where process A, running in user mode, jumps to the kernel to make a system call and then gets switched back to user mode. Whereas in the second example, we get A, makes a system call, but then because the system call blocks, we go to sleep, and that CPU becomes available to somebody else. So in the meantime, it looks like they changed processes and actually ran B and connected B to that particular CPU. So context switches involves the switching of a process from one CPU to another. Let's see, and it's just going through the example I was going through here. This context switching, again, keep in mind when I connect to a CPU, I've got this secondary cache. If B comes in and uses my secondary cache while I'm sleeping switched out, when I come back in, I have to reload that 4 megabyte cache. And that gets charged to me as user time. That is not system time, even though it was the fault of the CPU scheduler for kicking me out. So in Irix, we have ways of locking things down into a CPU such that nobody can kick them out. So when a context switch is performed, just like on a Cray, we dump off A registers, vector registers, B registers, program registers, stuff like that. The exchange package mechanism is the hardware piece, but then there are also software things that we had to dump off. And a lot of that was done through vector registers, but not as an exchange mechanism. So the kernel saves the context of the currently running process and restores the most eligible process to run as specified in the run queue list. And we're going to look for CPUs that have been scheduled, or processes that have been scheduled on my CPU first. Then we're going to look at nearby CPUs. Then we're going to go across the topology for looking for work. There's also a separate run queue for real time. We actually have two different run queues. We have a local run queue for everything except real time. And then there is a global runtime queue. Because with real time, we don't want affinity. If a CPU comes up available, we want the real time to get scheduled to it as quickly as possible. So a context switch can occur if a process exits and another process needs to be selected from the run queue. If the process terminates and does an exit, stop in Fortran, then we're giving up the CPU and a process switch will occur. If the process puts itself to sleep pending an event, like it did in a system call, such as asking for I/O or memory, it's then going to go to sleep with that wait chan address being the event that I'm waiting to be satisfied before I get reconnected. Also, if the kernel is returning to user mode from service a system call, the process issuing the call is not the most eligible process to run. One of the things we've always said in tuning is stay out of the kernel. The more you go into the kernel, the more you're at the mercy of the kernel giving the CPU to somebody else. Okay, so these U names or get times of days can be very bad because every time you go in, it's called a voluntary context switch. Voluntary context switch says I made a system call which left me wide open to being switched out. Involuntary context switches are when the clock interrupt pushed me out of the CPU. But it wasn't my fault, it was clock interrupts, not the system calls. So if I do lots of system calls, I may be context switched out a lot. And lastly, when the kernel is returning from servicing an interrupt or an exception, we may have a context switch. Basically, every time we go into the kernel, when we're coming out of it, we do a process analysis and decide whether we're going to switch back to the same process or to a different process. Or we may actually be switching to a kernel thread now. VHAN, for example, is a kernel thread. It's a multi-threaded kernel now, such that we've got SPROC implementation for the kernel. And BD Flush and VHAN and a whole bunch of system daemons run in kernel space. They no longer show up with PS. They're not considered user space processes running with root permissions. They're now considered multi-threaded subroutines of the kernel itself that I'm jumping off to. So primarily, for example, two things are driving me out of the CPU and driving context switches. One are system calls, one are clock interrupts. And a lot of times when those SGI naps are going crazy, your context switching is going up right with it, because I'm releasing the CPU intentionally. The whole purpose of an SGI nap is to allow somebody else to get into my CPU and do a context switch. Unfortunately, if there's no one else there, I may release the CPU and it may give it right back to me, and then I release it again. And I sit there thrashing, saying, "Would you give the CPU back to me? I can't use it. Here it is back again." And then the kernel says, "Well, there's no one else to give it to, so you get it right back." And then you say, "Well, I can't use it," so you thrash and do an SGI nap again. And it's not uncommon for me to see that as a problem, this SGI nap. It's basically an indication of what's called barrier synchronization. Barrier synchronization is if I've got a multi-threaded loop, I'm coming along into the serial portion of my code and then I hit some sort of do loop. I'm going to do this thing a certain amount of time. And multi-threaded applications try to divide that do loop into different, what are now called threads. Okay, and each one of these threads will break up. For example, I've got a master thread here, and then I've got 1, 2, 3, 4, 5, I should make it 6. And then I've got 6 threads that I'm breaking that do loop across. Okay. Barrier synchronization is the phone tag that's occurring between each of these threads. So one thread gets finished with its work and checks with the other thread, "Are you done with your work yet?" Okay. And in the simplest mode, it's called simple threads. In simple threads, you just sit there thrashing, saying, "Are you done, are you done, are you done?" And your user time goes crazy as you spend all your time checking with the other threads. And by the way, I was surprised about this. SGI and the developers put a lot of hardware support for cache coherency, but they didn't put deadlock interrupts or semaphore registers in there. There's no hardware support for barrier synchronization. We have that on all Cray product lines since Steve Chen designed the XMP. Hardware support to break another CPU out of it, a deadlock interrupt to say, "Break out of whatever you're doing, I need to talk to you." It's like breaking in on the phone line, you know, and getting this little beeping saying somebody's trying to get a hold of me. So with simple threads, I just sit there playing phone tag, keep trying the guy and leaving a voicemail saying, "Are you done, are you done, are you done?" There's now what's called dynamic threads. And with dynamic threads, that's when we start doing the SGI nap. So when I go to dynamic threads, my user time goes down because I'm not playing phone tag, spending all my time reading barrier bits that sit in memory. Now I read the barrier bit, sit there for a little bit of time with block time, and then release it with SGI naps. So when I go to dynamic threads, I start getting higher system time because of that. Simple was the default in 6.4. Dynamic is the default in 6.5. And if you're undersubscribed, simple works best. If the only thing I'm doing is reading satellite data from Mars or something like that, one application on the system, simple works best. But if I'm oversubscribing the system, dynamics works best. And because a lot of the large compute origins are going into compute markets, traditional Cray markets, they changed the default from simple to dynamic. Simple is kind of the way the T3D worked, whereas dynamic is the way Unicos has always worked. There's no guarantee as to the number of CPUs you get. It's based upon the load on the system. And again, Unicos has had the same problems we have with dynamic, where we may have high system time because the application is spending all of its time trying to synchronize and not actually getting work done. And this is where multi-threading really has to solve problems. There was somebody running around comparing an IBM SP2 and saying it scaled perfectly. And then there was a little dagger down in the corner that said, "This does not include synchronization events." Which means, yeah, it's going to scale perfectly if you take out the time it takes to talk between threads. When you start multi-threading, it's going to take more CPU time because you have to spend time communicating to all your threads. So that's synchronization time. And if barrier synchronization breaks down, if these threads are not able to talk to each other, then you're in trouble. And in the Cray world, we created what is called gang scheduling, and gang scheduling says that all these threads will be on the phone line at the same time as a party line. Okay. In the Irix world, they got rid of gang scheduling. It's basically obsolete now. So there's no guarantee that all threads are going to be connected concurrently, and therefore when they're talking to another thread, the thread is actually there connected to a CPU and able to reply. So this is a real common problem. The number one problem out there is thread barrier synchronization problems. And this is costing a lot of CPU time at some of our sites. Anyway, let's see. I think that covered everything there. So context switching primarily at these sites is being driven by the SGI NAPs being used for dynamic threading. Now when these processes are created on the system, we have what's called a PID, the process ID, which is basically the number or the slot in the process table. SCED is the first one created, so that has a PID of 0. Init is next as 1. And it's listing here vHAND and BD flush, but they are no longer system daemons. If I go off to my, let's see, 6.2 system here, I see SCED, init, vHAND, BD flush, mun LDD. VFS sync is flushing my inodes out to the file system. There's an unmount daemon, there's shake D. PD flush is actually pushing memory pages that have been pinned in memory out to swap. So all these things are showing up as daemons that are really processes with process table entry slots to them that PS is showing up. But if I go to a 6.5 system, they will not show up there because they are now within the kernel. So I still have daemons, but I don't have vHAND, I don't have BD flush. They don't have process table entries as such. However, if I go into crash, let's see, iCrash in Irix, I can do, let's see, sthreads. So the sthread command is a threaded system now, so with sthread I see these same things now, except they're in kernel space rather than in user space. So they're not processes with root permission, they're actually threads of the kernel itself. So there's my shake D, there's my vHAND, those sorts of things, but they were not there with the PS command. So there is an option with Systune to go with the old technique where it would show up with PS, but there's no reason to do that. So a lot of these daemons no longer exist as daemons with PIDs anymore. And in this example, they're also showing a Getty and a Telnet and a few other things, all having their own PID. Eventually, the PIDs will wrap. The configured number, I think, by default might be 99999, but Systune allows you to up that. And then you go wrapping back around. And the PID is what I have to use with the kill command. Yeah, it mentions down here these system daemons were implemented differently as system threads rather than as daemons running in user space with root permission. And so they're no longer displayed with PS. So here's a PS command, and I think we've all seen that enough times. And again, the parent PID, if my parent gets killed, I get inherited by init. So there may be processes out there that have a parent PID of 1. So as I log out, if the parent shells are dead or whatever, all orphans are inherited, picked up by the init process, and we'll have a parent PID of 1. Yeah. Nothing else of interest there.
What are the
Go ahead.
question marks?
Meaning that it's not tied to a terminal. Okay, there's no terminal connection. Standard or standard out, standard in, we're closed off, for example. NQS jobs, if I did an ampersand sign and logged off, or no hop and logged off and logged back in, so they no longer have a terminal connection tied to them. But NQS jobs, LSF jobs, we're seeing system daemons here, things like that. There's no terminal associated with them. The other one we have here now is process group IDs, so that when I have a group of processes, I can kill the entire group. Process group is a set of processes that are related to each other by some common ancestor. For example, in this example, they've got the shell that has a process group ID of 798, and then everything I do in my interactive environment is going to have that parent process group ID. Okay. So I may both have a parent PID of 798, and then all the processes may also have a process group ID of 798. And for example, in this one, they forked off BG1 to BG-CLD1. CLD1 would have a parent PID of 27105, but it'd still have a process group ID of 798. Now in Unicos, we actually keep that information in the session table, and if that process group exceeds limits, we can send a kill signal and kill the entire process group. In Irix, they don't have that ability yet to have limits by process group. You can change your group IDs by using a set PGID or set P group ID system call. And some of these things are more commonly used in, for example, MPI, message passing interface. And now they're doing a PS-EF, the F giving me a full report. And now I see both the PID, the parent PID, and also the process group ID. And a new metric in here called the session ID. Note the session ID and the process group ID are consistent here. Okay. So the session ID is basically another handle for everything within that process group. And in fact, you can do an SID command. Let me quit out of here. If I do SID, it will print out what my session ID is in hex, and also project accounting if I have a project ID. And project accounting is like an account ID in ACID within Unicos. It's not uncommon in, for example, the aeronautic industry that an engineer is designing a wing for the Army, the Navy, and the Marines. And they'd be three different billing accounts. So they'd have 3 different project numbers. Unfortunately, Irix doesn't schedule based upon project IDs. In Unicos, Fair Share will look at account IDs to decide who gets the resources. But that's not implemented within Irix. So process group ID and an SID or an ASH or a job ID are essentially words for the same concept. So a job ID, a session ID, an ASH, or a process group ID. They're all basically the same thing. SID is the POSIX compliant name for it. And there is a session table within Irix that keeps track of all attributes about that session, except for limits. It's got what it's used, but it doesn't have limits. So if I exceed my limit, the kernel can't recognize that and kill me. That will be implemented in another year within Irix, such that the kernel will have limits within the session table as well, and if the use exceeds the limits, then I send it a kill signal. And that way it can't abuse the system.
So the things that you tell us about that Unicos had that Irix does not, you're telling us because they probably will be.
Yes. Trying to map things.
It's a,
We put things into Unicos for a reason, and now the Unicos developers and Unicos MK developers are in charge of a lot of this stuff. The array services software, session IDs, accounting, a lot of these things are being ported and implemented within Irix. And one of the big things is job limits. Irix supports per process limits, but it doesn't support session limits or job limits. And that's something that our customers are asking for, along with something called the user database, UDB. And a lot of these things are appropriate in a data center environment, but not in a workstation environment. So those sorts of things are being implemented by the Egan software developers. So most of your functionality in Unicos will be implemented. Unicos MK, that's going to be another battle. For example, in Unicos MK, there's a kernel scheduler called psched. Big battle between that and Miser and what's the best way to schedule resources and stuff like that. So there may be changes as we go along. But a lot of the data center features that we added into Unicos are being implemented in Irix. For a reason. Our customers want it. Unfortunately, it's not volume customers. It's high-paying customers, but not volume customers.
So are these options at install time, or they're not used?
I don't know yet because like the user database will be another year. Some of them will be, like CSAM, the SAM utility is going to be implemented. TSAR is going to be implemented. Those would be unbundled in separate images. But then things like primary, secondary partition allocations are built into the kernel and would not be something that you could isolate from. So it really depends upon the feature. And when I first started working in Irix, I went to the developers and gave them a list of 3-4 pages of things that I had in Unicos that I needed in Irix. But at the same time, there are things in Irix that I wish I had in Unicos. So other than the parent process, the parent ID, the process group ID, we then have the session ID. In the Cray world, we always called these jobs, but that was based upon IBM and controlled data where we called them jobs. Along came POSIX and said, well, job is not Unix-like, it's IBM-like. So instead they created the concept of a session. And a session is essentially a log in, do your work, and log out. Or an NQS request would have a session ID associated with it. So it's all the work associated with the parent that I had to get my work done with. So I may have compilers, I may have loaders, and I may have the actual execution run. Those are 3 different processes it took to get my work done, all with the same session ID. And they're showing here that the session ID is mapping to the parent process or the process group ID. And again, when a user logs off, the user's shell is terminated. However, the user may have other processes running in the background. I may have done a no-hop, something like that, and those things will still running, having that session ID until they actually terminate. And however, running in the background, the kernel has to deliver a SIG-hop signal to each of the processes belonging to the session to notify them that the session is ended. But you have the ability with the no-hop command to say ignore the SIG-hop and let the thing continue running. But normally that's going to terminate the remaining session processes when I log out. If you've ever fired off things in the background, you try to log off and it says you've still got jobs running or something like that. You can continue to try to log off and they may be sitting there running without a parent, or you may kill them or reactivate them, something like that. So they did a PS, and with the J option for job IDs, you get the session IDs. And I'll point out also then that when you're using Miser, the parent process ID is also part of what's called the batch ID. It's all the same thing. It's different names for the same handle. So now with Miser, you've got a batch ID, which is your parent process ID or your session ID. Different names for the same thing. So with a -J, I then can see the session ID for all processes on the system. Now what I wish I had was the ability to consolidate just by session ID. So for example, top. If I had an application that was 128 threads wide, I'd like to consolidate that down into one line and say, here's how much work that particular session is taking from my system. Because I don't have 128 lines on my screen to be able to see everything that's running. And as the systems get larger and larger, you need to start collapsing and consolidating down by workload units that aren't by process or thread, but more of a job concept or session concept. So process creation is the fork process. Ged forks to create init. Init forks create the geddies. When you log in, inetd is going to fork off telnetd for your session. And then telnetd is going to fork off the shell based upon your password file. And then your shell is going to be forking off and execing the individual processes as you run. So fork is the beginning way of creating processes, but again, sproc is another way. And even in Unicos, we've got like vfork and other ways of creating processes, different implementations. And different vendors have different ways of creating things other than a fork, because a fork is rather heavy. And again, I mentioned before, I could have a gigabyte process that tries to do a tape mount call system, which is a library call to fork a child and execute it. And in the Cray environment with Unicos, we created vfork so that the child doesn't need a gigabyte of memory in order to go through the fork process to size back down to what it needs for the tape mount command or something. Let's see. So it's just trying to say here that sked does the initial, but everything in it is the ancestor of every process on the system except some of the daemons. So every process except some system process is initiated by the kernel or created either with fork. They may exec on top of them the actual executable, but the fork is what creates the process table entry. There's a routine within the kernel called newproc, which creates the process table entries for you and sets up all the kernel structures like user.h for that individual process. So in simplest terms, a user process makes a fork request to create a new process called a child. The newly created child is basically a clone of the original parent. It has the exact same environment. Any files that were open in the parent are open in the child. The file descriptor table was copied with it and stuff like that. Let's see, so it appears that the child and parent are the same resulting from the fork. And the only difference is that they have different PIDs. They have different parent PIDs. Some of the accounting of the child may be initialized to 0. The child will not inherit any locking mechanism. It will inherit open files and open service sockets, network sockets, but it will not inherit any locks. And then after the fork is complete, both the parent and the child return from their individual fork to continue execution. Usually in the application after the fork, we then exec some application on top of us with the fork. Okay, so most forks are followed by some sort of exec. And you could have problems where it may take a while for the fork to occur, for example, a memory shortage. And during that time, it may show up as the same as the child. It may have same PIDs and everything until that fork is finished, until I get all the memory that my child needs. Okay, so it may not be uncommon for you to see, for example, SH. And even on Unicode, the same thing happens. If I oversubscribe memory, it'll show the parent until the fork can get all the memory that it needs. Then you see it change to the child. And if there's memory shortage, it may take a while for that fork to complete. This will show up as S-break time within Irix. If forks are taking time to get their memory, that's going to show up as S-break time. And in 6.4, I used to see it a lot. In 6.5, I haven't seen it. So here is the C code where they're setting a exit status on the return. I'm then going to do a fork. The fork could fail. The fork could fail because there's no memory on the system. It could fail because there's no process table entries. There's also a limit max up in terms of the number of processes per user. So if I exceed that limit, my fork may be denied. In the NQS market, it'll actually start shutting down NQS queues when forks are failing. So you always want to check your return status. And typically a little bit after the fork then would be some sort of code to set up the next environment, then actually overlay and exec the executable that they actually want to run. Yeah, we went through all that. So when the fork returns from the kernel, the parent and the child have identical copies at their user level, except for the value returned by the fork. And a child inherits the CPU scheduling priority from its parent. Whatever attributes the parent has, the child has. And it's also pointing out here that during the fork process, it's not so much the fork, but when it forks the child, any files the parent process has to open for processing before the fork will be open in the child. So the child will open all the files that are open. You don't have to reopen anything. Now systems impose a maximum number of processes on the system called nproc. And with systune you can change that. And then max up is per user. I had a recent system I logged into, max up and nproc were set to the same. And one person then filled up the entire process table and everybody started getting forks failed. So you do not want max up to be the same as nproc. In the Cray world, we're typically at a default of 25 for max up. With user databases, typically 25 processes that you can fork off before you hit a limit. And when user database is available, then we'll be able to set a max up on a per user basis rather than enforcing the same limit on everyone. Check my time here. 5 more minutes and then we'll head out. So they're trying to show process creation here. The CPU creates the parent. The parent has a PDA. It has a thread structure. It has a proc structure. And it has credentials that are pointed off to by the proc structure. Then during the fork process, the parent is going to create a child. The child will have new proc structure entry showing up with PS. It'll have a new credential area. It'll have its own private regions. But note the private regions are pointing to the parent's data and the parent stack until the exec actually occurs. And the text portion may be actually pointing to the exact same text. So on a fork, the kernel figures out if it's necessary, if the necessary resources are available to clone the child, clone the parent. So it allocates control structures for the child. There's going to be some allocation in the thread structure, which was basically user.h. The proc structure, which is your process table. The credential structure, which used to be actually in the process table, but it's been spun off as its own structure. And it's also got to create the p region, the page table, some other user.h structures, and a few other miscellaneous things. None of these things are directly manipulated by the process. They're all structures used by the kernel to keep track of the process. So the child's control structures are then initialized from the contents of the parent. If I had open files in my user.h, the child is going to pick up that same attributes. A unique PID is then assigned to it. The parent PID is set up. The kernel sets all the reference counters for all the files which are normally associated due to inheritance. Any open file prior to the fork will remain open. And then the child is added to the run queue for selection by any CPU to receive a time slice. In a demand paging environment, memory is not automatically allocated for the child at the time of the fork. This is another advantage of a paging system. I can go through that fork process quickly as long as I don't touch the data. So this 1 gigabyte process is going to be able to get through that fork rather quickly compared to a cray. In fact, on a cray, the nschedv parameters may not allow the fork to complete, and it may sit there sleeping for nschedv-h to get set or something of that sort. So when a new process is created, its image is almost identical. The kernel accomplishes this by providing the child process with a copy of the parent's page tables. In other words, the child's page table points to the same physical memory pages as the parent as a result of the fork. But now the parent's pages are not actually copied and given to the child at the time of the process creation. Rather, the parent's process data and stack segments are marked as what is called copy on write. And copy on write is simply a way of getting through the fork process more quickly. So both the parent and the child processes share this copy on write space. If I'm going to exec immediately and I don't touch that copy on write, it's fine. Okay? No program fault or anything like that. So if either the parent or the process tries to write to a copy on write memory page, a fault occurs and that page is copied to a new page of memory. Typically, we don't do much memory referencing between the fork and exec, but it could happen. And let's see, in this situation, the parent and the child will have their own private copy of that memory page that was not created during the fork process, but because I touched it, I tried to write to it, I made a copy of it. Again, the parent and the child will always share text pages unless either invokes the exec system call to load a new program to execute. So it avoids the memory management scheme, the copy and write, avoids the need to copy the parent's pages of memory every time we do a fork. It's when we do the exec that we have to start dealing with the process size. So you get efficiency by considering the shell process, which issues forks repeatedly. The shell, every time I do an ls or whatever, is going to fork off a child. That way I don't have to create a copy of the image space that that shell may have and actually save space. Another example is inetd that's constantly forking. So a lot of this stuff is appropriate for an interactive environment where I have lots of forks and execs going on. But in a batch compute server environment, I typically don't do a lot of this. Fork creation, process creation does not occur that quickly because I run for a long time. We then terminate the process when it's done. This is done through an exit. So when you do a stop in Fortran or return within C or exit, you're going into a library routine that makes a system call named exit. And in the process of exiting, we're going to immediately release the user addressable space. And from that point on, I call it a zombie. A zombie is basically a process that's been lobotomized. Its user addressable space is no longer usable, it's no longer valid, but the kernel has all kinds of structures and memory resources committed to it. Okay. How many people have seen zombies within PS and stuff like that? One of the things that can happen here is if you've got a counting turned on, in the process of going down to a zombie, I'm going to ask for file system buffer cache buffers to write accounting records in. If those buffers are busy because everyone else is using them, I may stay in the zombie state for a while. And having zombies sitting around on your system could be a good indication that they can't get the resources they need to continue freeing up the structures, including doing this accounting type of stuff. Okay. So in that case, you start getting a pressure on the process because the file system buffer cache is busy, I can't get the buffer, and my elapsed time keeps elongating even though none of that's real work. I'm sleeping waiting on a file system buffer cache buffer. If the system goes into a hang state, we never go through the exit. We're off in la-la land. So a process can terminate due to the exit system call. It can terminate by returning to its main, or it can involuntarily terminate due to receipt of a signal such as a kill system call. So when it exits, it becomes a zombie. It releases all of its user addressable space, but proc structures and things like that remain on the system. And it's going to be marked as a zombie until all the kernel structures are gone. Let's see. And zombies, by the way, orphan children are inherited by init, and they will have a parent PID of 1 when they're a zombie, because their environment is no longer there. Now, we do have the ability of waiting for a process to terminate. This is, for example, what the shell does. I fork, exec, and then wait. Okay, so the shell is sitting there in a wait state saying, is this child done with its work yet? And for example, with the ampersand sign, we fork it off into wait, and then we constantly go back and check to see if that process is terminated. So by default, we wait for the exec to finish, but if I put the ampersand sign on, we go to a wait system call, and our parent goes to sleep waiting for the child to finish. Let's see. And again, zombie processes, parent issued a wait to wait for it, or the parent of the zombie terminates and the zombie is no longer needed. And PS reports zombies or reports processes. It typically shows defunct for command name. Okay. And I'm pretty much done here. I'm just seeing where else I need to